Okay, so perhaps we can start. So when I was a high school student, I read a book by Ukichiro Nakaya entitled Snow, the simple title. And Nakaya was a physics professor at Hokkaido University before the World War II, and was the first person to succeed in producing artificial snow crystals in a laboratory. He found a relation between crystal shape and temperature and vapor supersaturation of the air, and summarized the relation in the so-called Nakaya diagram. In the last chapter of this pedagogical book, Nakaya wrote that by studying crystal shapes of snow, one can infer the atmospheric condition in the sky, and ended the book with a famous sentence, "Snow is a letter from the heaven, and it's encrypted in its shape and pattern." So Ken Libbrecht is bringing this science of snow crystal to the 21st century. So Ken is a lifer at Caltech. He was in the class of 1980 and shared a room with Star Finney at the Page House. And Peter Goldreich, I understand, was a resident associate of their house. He went to Princeton to receive his PhD in 1984 under supervision of Robert Dicke, and returned to Caltech as an assistant professor in the same year, skipping a postdoc. He was made a professor of physics in 1995 and was the executive officer for physics for 16 years until 2013. And I'm told it was longer term than that of Stephen Fauci. He has worked on a variety of areas in physics. When he arrived at Caltech in 1984, he started working on helioseismology at the Big Bear Solar Observatory, for which he received the 1991 Newton-Lacey Pierce Prize from the American Astronomical Society. He then made a transition to AMO and to laser cooling and trapping. He was involved in LIGO instrument development for 15 years until 1914. And since 1997, he has been working on ice crystal growth and is currently focusing entirely on it. Last fall, he completed the 523-page monograph reviewing his work on snow crystal growth over the past 2 decades. In an article in the Quanta magazine of the Simons Foundation, which also appeared in the last fall, a French physicist was quoted as calling him the Pope of snow crystal. So Ken is active in public outreach. He published 8 books on snow crystal and received 2004 Benjamin Franklin Book Award for one of them. The U.S. Postal Service and the Swedish Postal Service issued postage stamp sets using his photograph. The U.S. set sold 3 billion copies in one season, which I guess is like 10 copies for each person in this nation. Ken was a consultant for Disney Frozen movie in 2013, which featured scientifically accurate snowflakes and won an Academy Award for the Best Animation Feature Film. He was not a consultant for its last year's sequel, Frozen 2, which had lousy snowflake and failed to win an Academy Award. So I'd like to invite Pope Ken of Snow Crystal to the podium.
All right, well, thank you. Thank you for that lovely introduction. So I want to talk about how crystals grow, the physics of how crystals grow. And of course, I want to focus on ice because it's my favorite crystal. And so I'm going to start with an experiment, which I call a snowflake on a stick. And so the idea here is you create an environment in which snow crystals will grow. And so that means just a constant temperature, which is below 0, of course, so ice will form. And a fixed supersaturation, which is above 0. And the supersaturation is just like the relative humidity, except minus 100%. At 100% humidity, the air is saturated, so you need to be above that to grow crystals. And just to make life simple, there'll be air in the chamber, so just regular air at 1 atmosphere. And now in that environment, one can add a seed crystal to get the thing started. And instead of a little tiny grain of ice, which is a typical seed crystal, I'm going to use a long needle of ice. Okay, and these are typically around 2 millimeters long and very, very narrow, very thin, maybe a couple microns in diameter at the tip. And there's a whole story about how you make these thin ice needles, but I'm going to skip that for now and just say we can do this. There's some laboratory tricks. And so you take that needle and you stick it in this environment, and the needle gets thicker, and you can grow a snowflake on a stick. Okay, and there's the movie version of this picture. And so in the beginning, the supersaturation was fairly low, 16%, and it grew into a little plate. And then I turned it up pretty rapidly to 4 times that, and then it grew these dendritic structures after that. Okay, and the whole thing is sped up. It took about 20 minutes to grow that crystal. Okay, so the nice thing about this experiment is you can do it over a broad range of conditions. Okay, so you can really see what's going on. And so here we see different snippets of growth as a function of temperature along the horizontal axis and supersaturation along the vertical axis. And so here you can see from -1 to -21 degrees. And so each column is a constant temperature. And the lines are constant supersaturation going from 8% all the way up to 128% in factors of 2. Okay. And so each of these is a single crystal of ice. So the molecules are all lined up from one end to the other. They're all growing on these thin ice needles. And they're all growing under constant conditions, constant temperature and supersaturation. And so what I showed you before was here, starting around here. I made the plate, and then dendrites on top of the plate. And those kind of form your sort of holiday snowflakes. But you can see there's lots of other shapes. And so the canonical snowflake you see all the time is just a very small slice of the whole parameter space. So let's look at a few of these. This one up here at -5 and high supersaturation, it produces a kind of a woolly looking thing. It has 6 branches, and each branch has this kind of structure. This is just a drawing to kind of show you the basic idea. And there's these side branches and 2 prograde side branches and some retrograde side branches. I like to call this a fishbone dendrite because it kind of looks a lot like what you'd pull out of a fish. Okay. If you go a little colder, at -7, here's one, which is a cup-like crystal. Okay, that's hollow, like a cup, a sort of conical shaped cup. The edges, the top edges of this are quite sharp, like a micron, and so it just grows away like this, and you get some fins growing off the side. Okay, if you lower the temperature just a bit, a couple of degrees, it's something similar, but now the cup has sort of opened up, and it's more of a saucer. Again, the edges are quite thin, and the fins have sort of transformed into this sort of I-beam kind of shape. And so you see there's a lot of different kinds of morphologies. This is all very consistent. You can, and reproducible. You can just grow these things over and over again and get all these different shapes. And so the question is, the real challenge is just what's going on. I mean, how do you explain all of this? It's hard enough if you had one particular morphology you were trying to explain. That might not be too bad. It might be even better if you had, say, a slow monotonic change with temperature. But in this case, it's kind of crazy, and you have to try to make some sense out of this. And you can't just sort of write down the equations and plug it in, because we don't know what the relevant equations are. We don't know all the physics going into this. Question?
Sorry, quick question. Why don't you get growth on the rest of the ice needle? Why is it only the tip?
It does. There's a little bit. The needles do get thicker. They tend to be shielded by if there's a plate on top. Okay. But yeah, this needle is quite a lot thicker, for example. All of them are quite a lot thicker than when they started. Okay. Okay, so we're going to try to explain this. And that's sort of what I really want to focus on in this talk is, what do you do with this? Before getting into the physics, I wanted to say you can see this stuff outside if you happen to be in a cold climate and it's snowing. So maybe you're on the East Coast, or maybe you're going skiing sometime. You can go and look for these things yourself. And different structures. This is called a hollow column. And it's a little cartoon up here, which is just a cylindrical hexagonal crystal, but it has these hollow regions inside. And so they're kind of hard to see. These are maybe a millimeter or 2 in length. So it helps if you have a nice microscope. Here's my traveling microscope for photographing these things.
Does that grow from the top or the bottom or the middle?
It grows from the middle. It starts out as a solid piece of ice, and then it grows in this direction and in this direction and outward. Okay. So these hollow columns are never hollow all the way to the center, because it starts with a solid piece of ice. Okay. Anyway, my point is just you can go out and see some of these things for yourself. They really do fall from the sky. It's not just a laboratory curiosity. Needles as well are around -5 degrees. They're just longer, maybe 2 or 3 millimeters, a little more dendritic. And these are very common. You don't think of these when you think snowflakes. This does not pop into your head, but these are quite common. Here's a slide where I just put a microscope slide out and caught a bunch of crystals, and they were pretty much all needles. So these are easy to see as well. Here's a peculiar one that most people have never encountered, which is called a cap column. And what it is basically a column with plates growing on either end. So like 2 wheels on an axle. And several examples here. This one has got more complicated sort of needle crystal, and the plates are seen edge on here. And you can find these too. These do not grow under constant growth conditions. The column grows when it's, say, around -6 Celsius, and then it gets colder, and the plates will grow at around -13, give or take a few degrees. And again, if you go out looking for these things, you don't notice them, but if you know they exist and you go out looking when it's snowing, you probably can find these. They're not that hard to find. Of course, there's the canonical holiday snowflakes. These are the money shots. No one shows you those other pictures because nobody wants to look at those. They're not as fun as these. These are very beautiful, and they have this symmetry and complexity. They only form around -15 Celsius. That's 5 degrees Fahrenheit, so that's pretty cold. So if you want to get pictures like this, or if you want to see these crystals, you've got to be willing to stand out in the cold quite a bit. And I also just wanted to point out these are really thin and flat. This is a side view, which is why we call them snowflakes, okay, not snow globs, which makes them very fun to photograph too, because they're thin and flat, and you can get a very nice picture. So again, if you go outside, there's a whole menagerie of different crystal types you can see. People have given them names. There's lots of names. It's a little like naming bread. There's no specific kinds of names. People give them names just like talk about them. And but nevertheless, you can see all these kinds of things growing outside. Okay. And the question is, again, what's the underlying physics?
Would you say from time to time what scale is?
Time to time.
I believe it's millimeters.
Yeah.
But maybe it's 2 meter snowflake in one.
No, on this one, I 2 or 3 millimeters long.
So it's all kind of millimeter scale unless you say different.
Oh yeah. And these are all a few millimeters at most, up to maybe 5 millimeters, 3, 4, 5 for these. Okay, but yeah, people. Okay, that's all. So let's talk about physics. First of all, where do these come from? Let's talk about natural snowflakes. They come from clouds, of course. Everybody knows it snows from the clouds. What are clouds made of? Clouds are made of liquid water droplets, kind of micron scale droplets. And as a cloud gets cold, so it forms usually when it's fairly warm, and so the droplets are liquid. And as the cloud cools, it will start to freeze, but not right away. You usually have to cool a cloud below freezing quite a bit, maybe 5 degrees below -5, -10. And then the droplets will start to freeze one at a time. And if a droplet freezes, it will start to grow. And it will absorb water vapor from the air. That's how a snowflake grows. It absorbs water vapor. And the droplets around it will start to evaporate because the vapor pressure of supercooled liquid water is higher than the vapor pressure of ice at fixed temperature. And so this thing will grow. And it takes maybe about 100,000 droplets evaporating to make a good-sized snowflake. And eventually, then these fall to the ground. Okay, so getting into the details, the first thing you really need to look at with snow crystal physics is the attachment kinetics, and this is just the crystal growth term for just the process of molecules sticking to the crystal as it grows. Okay, and if the attachment kinetics is highly anisotropic, you can get facets. That's what happens with ice. And to see that, you just look at a little grain of ice. Okay, there's a little molecular model. And this is being bombarded with water molecules all the time. And if the surface is very smooth on a molecular scale, so there's not a lot of molecular bonds that are free, then a molecule that hits that surface may not stick. Whereas the rough regions, where there's a lot of dangling bonds, the molecules will stick more readily. And so if you just take this kind of randomly shaped crystal and let it grow for a little while, the rough regions where the kinetics is very strong, the attachment is high, will fill in and the faceted surfaces will not fill in, and so you get, in the end, a faceted crystal. Which surfaces are facets depends, of course, on the molecular structure and the bonding and how many bonds are available during the crystals. And so for ice, we know the structure of the crystal for a long time, and there are two principal facets, the basal facets and prism facets, shown here. And this little hexagonal prism, that's kind of the hydrogen atom of snowflakes. It's the simplest thing. There is kind of a misconception that the reason you have facets is that the surface energy of those surfaces is low. But that's not true. That's not really very little to do with it. Surface energy is not very important in this context, and it's also quite isotropic. The equilibrium shape of an ice crystal is basically spherical. So the surface energy is not so important, but the kinetics is important. And, you know, surface energy is an easy concept, and the kinetics is hard because it's a dynamical process. And so we have to try to figure out what's going on. But it's the attachment kinetics that's doing the work here. Okay. Second piece of important physics is diffusion limited growth. There's a lot of literature on diffusion limited growth, so I'm not going to try to survey all this. But in the case of snow crystal growth, it's particle diffusion, and that can produce a branching instability, which produces a lot of the structure in snow crystals. And to see that, let's imagine we look at this hexagon growing. Okay, so the hexagon is growing away, and the molecule, and it's removing molecules from the air around it, which depletes the air. Okay, so the supersaturation goes down around the crystal. And so in order to keep growing, the molecules have to diffuse through the air from the surrounding medium where its supersaturation is high. And if these points stick out a little farther into the supersaturated medium, they will pick up more water molecules just by random chance. And that produces this positive feedback effect. So the points of the hexagon, they stick out a little farther, so they grow a little faster, so then they stick out even farther and grow even faster. And so what happens is you get like a small crystal, and it starts to grow, and at first faceting is kind of the dominant process. The attachment of kinetics dominates, and you get a faceted shape. But then as it gets bigger and bigger, the diffusion becomes more important. And then this instability, sort of, you go through a tipping point, and the instability will kick in, and then branches will sprout from the corners of the hexagon. Okay, so that's a branching instability. And if you drive the growth really fast with a high supersaturation, then this instability could just run amok. And then you get very highly structured dendritic patterns like this with lots of side branches. And they kind of just come and go randomly. They're growing like crazy. And at minus 15, you get a flat crystal. The basal surfaces do not grow very quickly, but the prism surfaces do. And so you get a flat crystal, and so the dendritic pattern is kind of a sheet, two-dimensional. At minus 5, on the other hand, you can get this fishbone dendrite. It's very a three-dimensional shape. And the reason for the difference is because it's not just diffusion limited growth, and it's not just faceting. It's a combination of diffusion limited growth and the attachment kinetics that produces the different morphologies. And so that's kind of the crux of what's going on, is you've got diffusion limited growth that produces structure, but then the attachment kinetics is somehow guiding the structure. And you have to sort of put all that together to understand what's going on. Okay. Just with those two pieces of information, you can kind of get some of the basics of your garden variety holiday snowflake, which is why they're symmetrical, so symmetrical, and why we like to say there's no two alike. So imagine just how this grows in a cloud. You start with a little particle, a little droplet, and you freeze it, and it grows into a hexagon. We talked about that. And branches will sprout from the hexagon as it gets bigger, and so you get 6 branches. But now what happens, this thing is just wandering around through the cloud, and the cloud is not a uniform environment. And so the temperature and the humidity are always changing as this thing is moving around. And so you can all kinds of things can happen. You can get like little plates growing on the ends of the branches if the humidity is fairly low, for example. And if the humidity increases, you can get side branches that sprout from the plates. And what happens just depends on the local conditions at every time. Okay, and so the final shape of the crystal when it hits the ground just depends on the whole history of its growth. Okay, just the temperature and humidity it saw as it was falling through the cloud. And so with the complex history, you can get a complex shape that includes both faceting and branching. But the trick is that the gradients are in the environment are very large, very small rather. It's fairly uniform on a snowflake scale, and so the temperature and humidity across the snowflake are nearly constant. Cloud is huge, and so the branches all see the same conditions at the same time to pretty good approximation, and so so they all kind of grow in synchrony. And so, for example, here you see there was a bit of a faceted arm here, and then all of a sudden it started branching, and you got 3 little branches coming out. And the same thing happened here and here and here and here. And that's because at some point that crystal just meandered into a part of the cloud where the humidity was higher, and that promoted this branching. And so, it's not like the 2 ends of this crystal are talking to one another. They just see the same conditions at the same time. And because the shape of the crystal depends on the path it follows, no 2 crystals will follow exactly the same path because they're a turbulent atmosphere, and so therefore the crystals all look quite different by the time they hit the ground. Okay, so that gives you a sort of 2-penny explanation, but we still come back to this, and we have to try to figure out some of the details. You can see some of these things, like for example, at high supersaturation, there's a lot of side branching and structure. That's because the diffusion is important there, and you get this branching instability, which is really kicks in when you get high supersaturation. The growth is fast. Okay? Whereas at low supersaturation, you just don't get enough supersaturation to sort of get above that tipping point, and so you don't get any branching and just faceted crystals. Okay?
Unlike the cloud, this is, you can repeat this, right?
Oh, yeah.
Same conditions, you always get the same.
Yep, and these are constant growth conditions too. It's not changing with time. No. Okay. But on the vertical axis, you can sort of make some sense out of it. It goes from faceted to branched, and we sort of understand that at least some level. But it gets a little weirder along the horizontal axis because you can see it at high temperatures, just below freezing. You tend to get more plate-like crystals. And at -5, they tend to be more columnar in shape, or needle-like. And then -15, they're really thin plates. And so there are these transitions. And it's not monotonic. You have plates to columns to plates. And so you really have to, kind of a lot to understand in here. And it's not a simple thing because it's not just doing a nice, easy transition with temperature. It's moving up and down. And so to understand this, you really need to look at the attachment kinetics on faceted surfaces. That's sort of the key to understanding a lot of this weirdness. Okay? And another way to see that is another experiment. So we're just going to take a tank. It's maybe 1 meter high, just full of air. The whole thing's cold. And we put a little bucket of water at the bottom of the tank. And you heat the water, and so water vapor evaporates, and it mixes through convection with the tank, inside the tank, and produces supersaturated air. And then we have a nucleator, which we can make tiny little seed crystals. And then these crystals will just grow as they float around until they get heavy and they slowly settle down. And some of them will fall on a substrate, and we can photograph them. And you can do that over and over again. And so here, if you do this at -2 degrees, you see mostly plate-like crystals. At -5, columnar and very thin plates at -15. And Jeff, this is a 50 micron scale bar over here, which is the same for all the pictures. So these are pretty small crystals. Okay, but again, you see this transition from plates to columns to plates, which you have to explain. And this is a very old problem, as Hiroshi mentioned. Ukehira Nakaya first worked through some of these things in the 1930s in Hokkaido. Nakaya was literally the first person to look at a snowflake and see a physics problem because he was a physicist. And he was also the first person to make artificial synthetic snowflakes in the lab. And he did that over and over again and sort of mapped out, which is sometimes called the Nakaya diagram or the snow crystal morphology diagram, which just, again, has supersaturation on this axis, temperature on this axis. And you see plates, columns, plates, and sort of mixture here, and faceted down here and dendritic up here. Okay? And he published all this after World War II in this nice, wonderful book. It's just a fascinating read, a big, thick tome describing all the physics that was known about snowflakes at that time. And you get to the end of the book, and he sort of described this diagram, and there was no explanation for it. It was just an empirical result. And this ended up being kind of a puzzle for a long time. People tried in the 60s, tried hard to figure it out and didn't really make much progress. And in the 80s, there was another push to figure it out, and nobody really made much progress then either. And now I'm saying I've solved it. I'm just going to stand here and say I solved it. I'm not entirely sure. This paper is like 4 months old, so we'll see. It's a pretty new result, but I'm excited about it, so I'll tell you about it. Okay. And again, the attachment kinetics is sort of the key thing. You really have to sort of look at the physics of the attachment kinetics on faceted surfaces. So, a lot of times you're not smarter than the people that came before you, but you have better tools. And so that was my strategy all along, was just to make better measurements because we have better tools now, and measurements of crystal growth rates. So this is an example over here. This is growth velocity of a crystal as a function of supersaturation. Okay. In principle, the experiment's pretty simple. You just start with a little tiny seed crystal and you watch it grow. Okay, it gets bigger as it grows, and you just plot that and get a slope, and that gives you a growth velocity. And if you know the supersaturation in which this is growing, that gives you a point, okay, for one crystal. Growth is a function of, the growth velocity is a function of supersaturation. And then you do that for a whole bunch of different supersaturations. And you get a curve, a very characteristic curve, which has this functional form. And this is well known in crystal growth circles. This curve describes the nucleation of terraces, one molecule high terraces. Okay, and see what's going on, you just look at sort of this cartoon picture of what's going on the surface of a crystal. Lots of things going on. I mean, molecules are depositing, they're sublimating, they move around, they can attach, they can detach. But if there are no edges here to latch onto, there's just a flat, faceted surface, then about all you can do is nucleate a new terrace. Okay, that's how the crystal grows. You have to add another layer. And the way that works is you have these molecules sort of buzzing around on the surface. They sit there for a while. They'll pop off eventually. But if enough of them can get together and form a large terrace, that could be stable, and it'll just keep growing. But the terraces are not stable if they're too small. They'll just disintegrate thermally. And so if the add molecule density is low, these things will not nucleate very readily, whereas if it's high, they will. And that's what happens here. When the supersaturation is low, the add molecule density, surface density is low, and you don't get many terraces nucleating. And as you increase the supersaturation, you get more of these molecules buzzing around, and you're just statistically more likely to form a terrace, and then it will grow. Okay, and it's the growth, each time you add a new terrace, of course, that makes the crystal grow, and that's what gives you the growth velocity. Okay, now the theory for this goes back a long time. Nucleation theory was developed in the 1950s, and it turns out this parameter, so one parameter that defines that curve, is entirely dependent, almost entirely, on the terrace step energy, okay, which is just the energy of the edge of this terrace. And to understand that, you just look at the energetics of a crystal, because you know most of this already. The first line is the latent heat. Okay, what's the latent heat? Well, that's the energy it takes to vaporize a crystal. Okay, you got to break every bond. Okay, in this case, it's solid to vapor, so you got to take every bond and turn that thing into a vapor. And it's an energy per unit volume, because, of course, the amount of energy needed to disintegrate, to vaporize the crystal is just dependent on how much crystal you want to vaporize. The next line is the surface energy, sometimes called surface tension, especially with liquids. And that is the energy to take a crystal and just break it in two. Okay, again, you have to break bonds to do that, so it takes energy. And the number of bonds you have to break is proportional to the amount of extra surface you make when you break it. And so that's an energy per unit area. And so that's pretty well known, surface energy. And the next term is just the terrace step energy. And what that is we start with a little terrace here, this guy sitting on a thing, and we're going to sort of cut it in two and just sort of laterally slide those pieces apart. And again, we have to break bonds where that red line is, and that takes energy. And the energy is proportional to the line, the perimeter you have to make. Okay, so that's an energy per unit length, and that's the step energy. What's great about this is that all of these quantities are equilibrium quantities. They're just properties of the material. And so in principle, you can sort of understand this a lot easier. It's a lot easier to understand equilibrium properties than dynamical properties. And so anytime you can reduce a dynamical problem to an equilibrium problem, you're really making a big progress. So let's do that. Let's measure the step energy over a broad range of conditions. And the way you do that is you just do this. You make these measurements. You do a fit, you get that sigma 0 out, and from the sigma 0, you plug it into theory and get the terrace step energy. And here it is. Okay, we did this. Here's the step energy as a function of temperature for the basal facet and for the prism facet. Step energies only really make sense on faceted surfaces. Okay, so again, it's a single parameter. You can get a lot of information about growth rates from that one parameter. But what's funny about it is it varies a lot with temperature. That's not true for, say, the surface energy. Surface energy has a really mild change with temperature, 10% or something like that over this range. Not much, but here we see orders of magnitude a change in the surface energy. So how do we make sense of that? Well, here's a little drawing of the crystal. This is a projection, kind of a ball and stick model. And here's the step on the basal facet and the step on the prism facet. So we're trying to get the energy of that. And if you have an abrupt step like that, well, you can sort of see that in order to make a step in that sort of simple geometrical picture, you're really just adding a little surface right here. Okay, so the step energy should be kind of proportional to the surface energy. Just take the surface energy times the height of the step, and that should be a step energy, and that should be kind of what you get. And if you calculate that, that number is like up here, about the top of the graph, top of the slide rather. And so if you extrapolate this out to very low temperatures, you hit that number. And so the picture one can have in one's mind is that if you go to very low temperatures, everything's frozen out really hard, and this is it's an accurate representation of what an ice crystal looks like. It's just, the molecules are all just fixed in their little spots, and the step is nice and abrupt, and you get this picture right here. But as you warm it up, okay, now this picture starts to break down because there's a lot of thermal motion. We're very close to the melting point as we increase the temperature. And so the step starts to kind of broaden out, okay? It becomes a more gradual step, statistically more gradual. And so geometrically, you can kind of ask the same question, well, what is the extra surface area I'm adding? And if you make the step more gradual, the added surface energy is much less. And so therefore, the step energy, you might naively calculate in this very simple geometrical picture, will go down. And that's kind of what's happening here, is that it starts out as a very rigid step, and it just gets more and more smeared out. Okay, and on the prism facet, it smears out very low, and in the basal facet, it kind of levels out. Okay, and so this, of course, is not any real model. It's just kind of a cartoon picture of what's going on. But you can talk about making models of this because, again, this is an equilibrium quantity, and we can calculate equilibrium things. In particular, we have molecular dynamic simulations of ice. And in principle, you could put in and do a molecular dynamic simulation and calculate the energies in that and get step energies out, certainly as a function of temperature and a function of facet. People have not done that, but we're getting close. Okay, not me, other people. What makes this really great is that for the case of water, we have really good molecular dynamics models already. Why? Because molecular biologists care a lot about water. If you want to know what's going on with proteins or lipids or things like that, you got to put them in water. And so people have developed very sophisticated models of the water molecule interactions. And so therefore, very sophisticated molecular dynamic simulations. And they're just appearing now a few papers on using these models to calculate step energies, which nobody had done in the past. But, and you can sort of see the two most popular materials, silicon and ice. Okay. So let's imagine we can actually make these models. Then you have this really nice thing where you can kind of do a whole ab initio calculation all the way from basic quantum mechanics all the way to snowflakes. So we start with quantum mechanics. Well, we know how to calculate molecules, sort of, from quantum mechanics. We know how to calculate the interactions. Chemists have been doing that for a while, they certainly are making molecular dynamic simulations, so we know how to do that. We don't really know how to calculate step energies yet, but getting there. Once you have the step energies, you plug in, you get them from nucleation theory, and then you get growth rates, and so you've kind of gone all full circle, all the way from quantum mechanics all the way to snowflake growth. Okay. Again, this is a tall order. People have been making ice simulations for a long time, decades, really, like 30, 40 years, and they tend to look like this. This is at low temperature. where the surface of the crystal is fairly well defined, and it starts to look like this ball and stick model. When if there were a step there, you would see it. But as you get closer to the melting point, things get a little mushy because we're close to the melting point. You get a phenomenon called surface pre-melting, where the top layers, because they're not fastened on so well, start to become amorphous. And as you get closer and closer to the melting point, the thickness of that layer increases. And so, the terraced step is going to be down here somewhere, and it's going to be kind of mushed out. And so it's a hard calculation to do, but in principle, you could do it. Okay? But if you don't want to do it, you still already have the empirical measurements of step energies, and so we really kind of know a lot. The problem is if you want to explain snowflake growth, is this doesn't work. The morphology diagram, this is too simplistic. It's fairly monotonic, and it's not enough. You need some other physics. And so let's keep going. What you need is a new phenomenon, which you will not find in any of the crystal growth books, which I called structure-dependent attachment kinetics. Okay? It's a weird name for a weird phenomenon. And right now it's kind of a hypothesis, but I'll describe it to you because I think this is what's going on. And the hypothesis is just that on a large facet, you get kind of what's I call the normal nucleation barrier. Okay? The measured sigma 0 is in play, and you get just what I've been describing for nucleation limited growth. But the structure-dependent part comes in if you have a narrow facet. And narrow is sort of ambiguously defined, but where the top terrace gets to be order molecular dimensions, then the nucleation barrier starts to go down. Okay? But it's not very narrow. It's not like this thing is down to 3 molecules. It might be 100 molecules wide, and it still seems to affect the nucleation barrier and produces a lower barrier. So that's my hypothesis, and what it does, I'll tell you what it does before I tell you what it is. And what it does is it produces a peculiar kind of instability, an edge sharpening instability. Okay, so here's the idea. You have a crystal growing on a substrate, and if you grow that crystal slowly, what will happen is you'll nucleate new terraces on the corners usually. The supersaturation is highest at the corners. And these terraces will nucleate, and then they will rather quickly grow out and get large. And if you grow it slowly enough, you get basically what's called layer by layer growth. You make a terrace, it grows out. You make a new one, it grows out. Okay? But if you turn up the juice a little, make the supersaturation higher, then the nucleation of these terraces goes up. And the width of the top terrace goes down because they're just not moving out as fast as they used to. And so this kind of broad shape becomes narrower. And this is where the instability comes in. Now there's this feedback. You start with a broadish facet and the nucleation barrier is high, but then you turn it up and it becomes narrower. And as you make it narrower, the nucleation barrier goes down, so now it grows faster, okay, which makes it now even sharper. And so it tends to sharpen the edge as it grows. Okay, it's an instability. So it'll grow as a faceted shape until you hit some tipping point, and then it can go either way. It can go up or down, depending on whether this instability kicks in on the basal facet or the prism facet. On the basal facet, this would turn into a hollow column. Okay, the column would be faceted, and the edges will start growing, and then they grow very, very rapidly, and you get a narrow edge growing out here, which kind of stabilizes the whole thing, and you get this hollow column growth. Here you can get kind of a plate growing on the needle. So here's the needle at the beginning, and as it grows, this is an experiment, and this is the model. And as it grows, the sharpens like it does here until eventually this thing just sprouts out. And it's not the same as diffusion limited growth, but it's related. Okay, you need diffusion limited growth to sort of play a role in here, but it's really a different effect. It's a surface effect. And what this produces is rather abrupt changes in the anisotropy of the crystal because it's an instability. Okay, so the attachment kinetics will change abruptly depending on what's going on here, and that can produce rather abrupt changes in the morphology, and therefore these abrupt changes in the morphology diagram. And I sort of conjured this up because I was making models of these crystals growing, and you just needed something crazy like this to make it work because these abrupt changes just don't happen unless you have some kind of instability. But I didn't know what it was for the longest time. I mean, I sort of decided empirically that it had to look something like this. But only recently I came up with a model, sort of a microscopic model, which seems to fit the bill. So let me describe that. So let's look at a thin plate, okay, the edge of a thin plate. So there's basal facets here, the basal facet here, and then this is just the edge. Okay. Now, if you grow this slowly, then it wants to sort of sit near equilibrium because you're growing it slowly, and the surface energy will want to minimize, and so it'll be more of a rounded shape because that minimizes the surface energy. But as you turn up the supersaturation a little bit, well, there are nucleation barriers on the faceted surfaces, so they don't grow much. But the corners, there's no nucleation barrier, so they'll start to grow out a little bit, and they'll sharpen up. Okay? And that's because you put it in a non-equilibrium situation, and so it goes to a non-equilibrium shape. But the surface energy is still there, and there's sort of, therefore, a potential barrier, a chemical potential barrier that would really love these molecules to move over, and they could by surface diffusion. You would love to be able to take the molecules from here and put them on this facet because that would allow you to round that facet out again and lower the surface energy. But on a normal crystal, that won't work because that would involve surface diffusion on a very rough surface because this is a fairly rough surface, and that doesn't work. There's a standard result in crystal growth theory that you just can't have diffusion, surface diffusion over rough surfaces very readily. But if you have surface pre-melting, okay, all of a sudden now you've got this slightly amorphous layer sitting on top of all this. And the hypothesis that I'm saying is that that will allow this surface diffusion to take place, okay, just at the onset of surface pre-melting. Okay? And so what happens is if this takes place and diffusion brings molecules from those corners, well, these molecules are just going to flood onto this prism surface. And so the add molecule density on there will go way up. And even though I'm not going to change the step energy, the nucleation rate will go up just because I have a lot more add molecules than I would normally get. And so that can cause the nucleation barrier to sort of essentially go lower. And so if you look at a prism surface, at low temperatures, this diffusion is not allowed, and so nothing changes. But just when the surface the pre-melting kicks in, you can get this effect kicking in, and this diffusion turns on, and you get a big dip in the nucleation barrier until the quasi-liquid layer is so thick that you can't really even talk about add molecules anymore. The whole thing is covered with quasi-liquid. So you get a dip in the effective nucleation barrier. And then I'm going to say that it happens at a slightly different temperature on the basal and prism facet, which you sort of expect, but there's no real way to calculate this, so we don't know for sure. But, you know, a little theorist license, I'm going to put these where I want them. And now I put these curves on top of one another, and sure enough, I get plates here, columns here, plates here, just like in the morphology diagram. So it's a crazy theory. It's obviously very speculative. But I think it really works. It makes a lot of predictions, and so I'm doing some targeted experiments now, and so far this is really holding water. And there's just very little in the way of an alternative. It's hard enough to think of any plausible theory that'll do something crazy like this. And so this, I think, fits the bill. And like I said, it's a really nice quantitative model, so one can compare with real experiments and do lots of different experiments. And so that's the next step, is just testing all this, which I'm doing now. But this also produces a fairly self-consistent and comprehensive model of the attachment kinetics now, which we didn't have before. So now we can start talking about making 3D models. And that turns out is just a whole other can of worms, which is kind of interesting in its own right. But people have been trying to make models of growing crystals for decades. This was big in the 1980s, and it's never really gone away. And part of it is easy. Solving the diffusion equation numerically, piece of cake. But the surface boundary conditions are a little weird, and that makes life difficult. In particular, if you have a faceted crystal, that means the surface boundary conditions have these cusps, very cusp-like behaviors. And numerical models do not like cusps. Okay? And so as a result, nobody had been able to grow faceted and branched structures until 2008. And then it kind of opened up, and now people are doing it. There's different techniques. There's front tracking, which is sort of a standard diffusion equation solver. There's something called phase field method, which rewrites the equations. My particular favorite is cellular automaton models, which are easy to implement and run really well. And people have made lots of things that kind of look like snowflakes. But so far, these have been what I call morphology demonstrations. You write it all down, you do the code, and you put in some halfway decent boundary conditions, and you get something that looks like a snowflake, and you say, okay, it's done. But that's not the same as really doing quantitative models. And so there's a long way to go. But kind of proof of principle is there. And so now, because we have a model of the attachment kinetics over a broad range of conditions, we could put all this together, make real models. And that's to be done. But again, one can make a roadmap for really making models of all of these different things, and again, doing experiments, and not just looking at pictures, but making real measurements. And so you can do this whole thing from quantum mechanics to snowflakes. This arrow from the molecular dynamics simulations has gotten a little harder. We don't want to just do step energies. Now we need to know something about surface diffusion and pre-melting, and that's a hard step. So that's going to take a while. But again, this is a big thing in molecular biology, and so these tools are getting easier by the day. And so someday this will happen, but not today. But that's okay. We can sort of jump over that step because we have this semi-empirical model of the attachment kinetics, including this S-stack mechanism. So now we can plug that into numerical modeling. We know how to do that. And we know how to do this too. We just haven't done it yet, which is make 3D models. And we can compare with experiments. And with any luck at all, we'll be able to kind of iron out the details and actually get this so it kind of works. So at this point, people are always like, well, okay, this is great. What's it good for? It's like, are there any applications? It's going to make my computer run faster or something? No, it's not going to make ice skating better. It's not going to airplane de-icing, none of that. I don't have much to say here. It's just a problem, and I found it interesting, and I feel we ought to solve it. So I've been working on this for a long time, just kind of for fun. I like to think of it as like the rainbow, It's a phenomenon, you see it in the sky, and your first question is, whoa, what's that? And it took a long time to figure out how a rainbow worked. People figured out it was droplets, and they figured out there were reflections in the droplets, and the primary and secondary bows, and refraction, and Descartes got the geometry fairly right with caustics. The diffusion, diffraction gave these sort of supernumerary bows. Those are diffraction effects. And, there was sort of no eureka moment. It was really just a slow slog to figure all this out until finally the sort of theoretical and computational tools, mathematical tools became sophisticated enough that now you can just calculate rainbows all you want. They're perfect. Snowflake's way behind. We're kind of at the Descartes level. We're getting the rough ideas, so only 400 years to go. But it's just it's not that you have to know how a rainbow works. It's just that somebody ought to know that. So I started working on this. If you don't like that explanation, I can say that, okay, maybe the overarching goal is not to figure out how snowflakes work. Maybe the real goal is to just figure out how all crystals work, and particularly the molecular physics of crystal growth. And if that's the case, then I would say that ice is the best way to go. Why? Well, because all these things. It's a simple system. You can do a lot of experiments. You can look at both temperature and supersaturation. But the main thing is just that these molecular dynamic simulations are especially well developed in water and ice, which is, again, a kind of a spin-off of the molecular biology. And so really, this is just the best crystal to look at if you want to kind of understand the fundamental physics of crystal growth. But I tell you, you can sell it however you want. Nobody's going to give you money to grow snowflakes. Okay, so I feel this is good. I've learned to write this down when I give a talk, because the talk gets posted online, and I've got an angry email. It's like, you guys are wasting all my tax dollars on this silliness. And no, there's no tax dollars. I've never gotten any real money to do this. It's always been kind of a hobby. As Rosie mentioned, I've written a lot of books. The funding agencies have no interest in snowflakes, but the public, the consuming public, thinks this is a great subject. And so they buy books, and I get royalties, and that sort of keeps me in temperature controllers. And so I keep doing experiments. So I'll just tell you one application I have, which is an artistic application, which is I figured out how now to engineer snowflakes way better than ever before. Using, when I figured out this edge sharpening instability, I realized I could put that to good use by, if you put a crystal on a substrate and you tickle it in just the right way, which we know how to do now, you can make a plate grow on top of that crystal, even if it's quite thin, like 50 microns thick. And here's an example. You get a really thin seed crystal that's maybe 50 microns in diameter. And you start growing it, and a plate will grow on the top surface like this, side view. And so this plate, this whole plate does not touch the substrate. Only this piece in the middle is touching the substrate. Everything else is above the substrate. And then, of course, by changing the temperature and the humidity, I can make designer snowflakes. And let me tell you can make some just awesome snowflakes this way. Okay. When I was writing books, I needed pictures of snowflakes. You can't make a snowflake book without pictures. And so I had to slog out in the snow and get pictures because there just weren't any good pictures. But not anymore. Now I can make better snowflakes in the lab. I like to say they're better than nature. And I'm a connoisseur of snowflakes, I bet. One of the things I really find amazing about this is this whole crystal, which is maybe 2 millimeters from tip to tip, is all sitting on this little tiny nub. You can barely see it from the back row. And this one, too, there's just a tiny little kind of 50 micron nub. That whole thing is sitting on top of and balancing. I've never seen one fall over, which still puzzles me, but they are rather symmetrical. So one can grow lots of pretty pictures this way. And so these are good. These are the money shots. You can make lots of pretty snowflakes. And they're just better. They're more symmetrical, the sharper edges, just cleaner growth, anything what you get outside. These are the French champagne of snowflakes. That stuff outside, that's Diet root beer. So, and of course, you can make a lot of different designs. These are designer snowflakes. You can play around with it, grow different designs, different shapes, kind of on demand. It takes about an hour to grow one of these, so you can't just knock them out real fast. Of course, you can make movies. No reason not to make movies. So here's a crystal growing in the lab. This probably took about an hour to grow. Now, what you don't see in this movie, because you can't see these things, is you don't see the temperature and you don't see the humidity. And what you don't see is me just moving those things around like mad. Okay, so this crystal does not grow under uniform growth conditions.
What's the time scale for this?
About an hour. And so these are not uniform conditions. If I want to make this thing side branch, I'll say facet for a little while, then branch like crazy, and then facet. I'm really jerking it around a lot. And that's why it has this sort of really clean symmetry. Now this kind of fog you see on the outside is literally fog. Those are water droplets that condense on the substrate, which is just kind of below the crystal. That's because I'm blowing kind of moist air down on this thing to make it grow. And the droplets kind of come and go because they come and go as the supersaturation changes. So you kind of can see the supersaturation in the movie. Okay, so here's a thought. Let's make 2 seed crystals near one another. And now let's hit the go button. Oh, you know what's going to happen. Okay, they grow similarly because I'm applying them with the same conditions. And so you can get, lo and behold, nearly identical snowflakes. So people ask, is it really true that no 2 snowflakes are alike? Well, now I can say not anymore. It's not. So I'll stop with that. Thank you.
Yes, please.
So a question on this video. What happens if the seeds are close enough together that they start to merge?
Funny you should ask.
You don't answer.
I just happen to have that one next. You see, they interfere with one another.
Oh, okay.
And so you can make any kind of mess. It's hard to get a really nicely symmetrical crystal. Everything has to be tuned up just so. No, they usually don't. I mean, there's no water vapor right between them, and so they grow more and more slowly as they get near one another. Sometimes they'll merge. On the side branches, they'll sometimes merge.
Yes, Steve.
In some of the photographs you showed earlier, there were apparent deviations from six-fold symmetry. Small. Do you have any connection between those deviations and the statistics of your diffusion process?
What kind of deviations?
Well, it wasn't perfect like in your photographs of the designer.
Yes. Well, if there's any kind of imperfections in the experiment, you tend to get some asymmetry. Gradients, for example. It's hard to make a supersaturated environment at a constant temperature without some gradients, because supersaturation is a non-equilibrium condition, so you need to somehow pump water vapor into there in order to make it supersaturated. So it's hard to make a really pristine environment. In the wild, if you go looking in the wild, you can see 12-branch snowflakes. That's just 2 six-branch crystals that stuck together. There are even triangular snowflakes, which is another weird thing, but that's just because a 6-fold hexagon is not the most stable state. If you think about it, a triangular crystal is more stable. And so if you left them all long enough, the hexagonal crystals might become triangular. But we can make those in the lab, too. So, Jeff?
Yes.
Better in the lab. You need to go out and
You mean to what?
you're doing this now better in the lab, and you get a little too enthusiastic. You need to go outside.
But it's cold outside.
Well, is there a universal kind of character to this? You know, phase transitions of all kinds. There's a universality, and is there something about this? They're all different.
Yeah.
And,
You know,
and the morphology, the zoology is certainly interesting. But is there some common? You know, here's this. It's got a ratio-defined structure.
yeah, not so much. I like to think of the processes as being the fundamental part. Okay, the crystal structure is a.
So there could be a velocity.
Yeah, yeah.
Velocity.
Yeah, it doesn't really work that way. I mean, nothing scales very cleanly. It's a very complicated process. But, if you look at what's going on at the surface, that's kind of something you can think about calculating, and it doesn't change no matter how big the crystal is. The process of diffusion is a calculable thing. I mean, it's messy, but you can calculate it. And so I like to think of these sort of fundamental processes as being the fundamental part, and then as it gets bigger and more complicated, it just gets so complicated that, pretty soon you just can't describe it anymore. People often ask.
Brad in the back.
Yeah, you implied that to make these, you're actually dialing the temperature and humidity knob yourself.
Yeah.
Have you tried computer control, and does it make it better or worse?
Another level.
History.
It's on the list of things to do, but it takes a lot of time and money, and I just haven't bothered to do that. I've been kind of doing these other things. But no, I think it would make it better. But once you've grown a few dozen of these things, then maybe you say, well, I've done that now.
Okay, 2 more questions. So one here.
So if you understand this process well enough at some point, could you use that to weed out the history of a snowflake and use that to do metrology? If you saw a snowflake and you could see this pattern is from this temperature, this humidity, etc.?
To some degree, you can do that already. I mean, if you look at some of the morphologies, you can just point to the part of the diagram they come from and say, yeah, that crystal grew under these conditions. You could be more sophisticated if you want, but remember, most crystals do not look this nice. If you go outside, the average crystal is just a malformed piece of sand. So it's pretty hard to do anything real. People think that every snowflake is pristine and beautiful, but no, those are the photographers show you those really nice crystals because that's what you want to buy. And the really ugly ones, nobody shows you those, and they're by far the most common. So yeah, it's kind of hard to make sense because they're all colliding with one another, and just a mess.
Okay, one last question.
Yeah, so I was wondering, when you're doing these machinations with the humidity and the temperature, do you have some idea of what this is going to look like when you're doing that, or is it all kind of, you're just doing random motions and seeing what happens?
No, I have a pretty good idea. I mean, partly it's understanding the physics, and partly it's just making recipes. You dial a certain way, and you get certain kinds of shapes. And so it's very easy, for example, to make a branch crystal. I can sort of cause it to facet a little bit, and then cause it to branch, and do it again, and get multiple branches. And so I've sort of worked out schemes for doing things like that to some degree. What I have not done is make real computer models where you could try to understand that. That's the goal, is to really
track your emotions in these temperature changes and humidity. So you can
mostly I'm just playing around at this point. So this is an artistic thing. It's not. It's too complicated for science. First, when I do science, I can do little tiny crystals. They're very boring to look at, but at least you can make some real measurements. So.
Okay, I think we have had enough questions. And now, because this is a faculty colloquium, so we have wine and cheese at the patio downstairs. So please join us. Thank you.